Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with Learnbay.co. Happy learning!
So let's get started now. Okay, so people who have kind of studied under me, they will already know this. So I do prefer writing a bit more. So I might be writing a lot of equations or basically some derivations or even drawing things. So you are more than welcome to take notes. Okay, these will be helpful for you. So I would really advise you guys take notes. Okay. Okay. So fundamentally, I would like to say that neural networks are nothing but pattern recognizer. Can anyone tell me what is a pattern? Miss, we had discussed this in last Sunday anyways, but let's revise this. So what's pattern exactly? Or how do you can say that this is a pattern? What is a pattern?
Like if we have weather as cloudy or the tennis related problem was there, right? So if we
Okay,
have
okay.
weather, temperature, so based on that, whether we'll be able to play the tennis match or not.
Makes sense, makes sense. Anything else? Any other example?
To solve any problem, there should be a pattern.
So, really, Miss, to solve any problem, we require a pattern?
Not all the problem, some of the problems.
Like, but again, you have to give me the hallmark at least. Like, you have to tell me where it is important.
Okay, in
Like,
last class, you told us to find one of the number.
Yeah,
In that
exactly.
case, so in that case, it is required.
Okay, something else?
uh, like any pattern that is that is followed in the same manner for a long period.
Yeah, very good, long period. And if you understand this, basically, if you apply anything with uncertainty, so technically, if you want to do certain maths or like basically you want to come up with an equation of some kind with that, you are looking for a pattern recognition system. Okay, so what are the pattern recognition system that you already know? Means you have studied quite a lot of them by now, I guess. So what are these pattern recognition systems?
clustering.
Good, very good. Clustering. Anything else? Yeah, you can take almost any machine learning
Like
algorithm and you
linear.
can, yeah, basically you can say regression is a pattern recognition system. Okay. So fundamentally, what is regression or linear regression? What is linear regression?
Like if it's a line is fitted uh, across a linear, like it has a linear equation, then it comes under linear regression.
Yeah, so the idea is very simple, as you said, is like if I have host of points, fundamentally what I want to do, I want to fit a best fit line, or I want to get a best fit line here. Agree?
Yeah.
Okay. Hey, my voice is audible or is there any problem?
Yeah, it's audible.
Okay, all right. Let me know if something is off. Okay, all right. Okay, so anyone knows how linear regression works exactly? If I ask you, how does linear regression works?
Like it looks for the best fit line, which goes through the points.
Very good. But how?
There is a equation for the line
So
y
let's take
equal to
equation.
mx plus c.
Okay, good. Now
So m is the slope.
C is the intercept.
Correct, yeah.
So what next?
We'll try to calculate a MSC through all the points for the second line,
Okay, very good.
and
Why
then
MSC?
we'll try to reduce.
If I may ask, why? Sorry, why MSC?
Like we can go with the. It is the best fit line. Like positive and negative both values can be taken into consideration. Like in MSC.
Okay, let's take a idea of MSC. So what is MSC exactly? Mean squared error. So error is fundamentally the difference between the predicted minus actual, right? And if you wanted to take the squared and their mean, that is called mean squared error. Okay, one of the simplest reason why we take MSC is because it gives a very good curve, which is usually some kind of a parabolic curve. And basically, usually you only have to deal with a single global optimum or minimum. It's easier to basically converge. Okay. How do you know you have converged at some point?
The change will be very minimum.
Yes, the change will be very minimal. So how do we start this process? Means how the process starts really.
First, randomly initializing, calculating the error cost function.
Randomly calculating the cost function.
No,
No, I think you wanted to say
no.
something else.
Initially, starting with initialization first. Initializing.
So you start with random initialization of what?
Yes, random initialization.
Of what?
Theta.
Random initialization of the line y is equal to mx plus c.
Very good. Basically, you start with your hypothesis, and for theta 1, let's say, and theta naught, you randomly generate some values. Okay, mostly there are some floating values. And now what you do after that? Let's say this is 7, this is 2. So what do you do after that? After you take random initializations?
Then we'll calculate a MSC and we'll try to reduce that MSC with the time.
And how do you reduce the MSC?
Like we'll take a derivative of this MSC equation.
Very good. Why we are taking a derivative?
Like at some point the slope will be 0, like at minimum point. Minimum.
So of course that's the idea that when you go for an optimum, the slope should be 0.
Yeah.
But the problem is that initially randomly, because we just initialized it randomly, so it could be anywhere, right? So first, slope will give you two things: the magnitude, that how much change might be required, and plus the direction in which the change has to occur. Okay, so fundamentally you have to perform gradient descent updates, so one after another, and of course as it goes closer it becomes smaller. The hope is you will be able to randomly start from anywhere, but you will be able to reach to the minimum point, and at this minimum point you will have the lowest MSC possible. Okay. The idea is there's always some error, so you might not exactly get a 0. So a lot of people just simply say it will be 0, but which is not true. In some questions you just would not get it, because again all the points can never be in a line, because there might be error all the time. So it might not even be theoretically possible to get a 0, but you can get as lower as a value as possible. Okay, so everyone is with me so far?
Yes.
Yeah.
Okay. So if I wanted to write down simple steps, I could do something like this. Okay, so the point is to randomly initialize this. Now, of course, you will get your loss function. It is mostly represented by j of theta, which happens to be square. After random in it, you have to perform a gradient descent step where basically it is theta 0 or whatever the theta I is into theta I is equal to theta I minus alpha. What is alpha?
Turning rate.
Yeah, and what's the significance of learning rate?
How much like gradient descent like to move?
Yeah, means like why simply the gradient descent or the gradient term is not good enough?
Because sometimes we may stuck at some local minima to avoid that one.
No, that is not the reasoning. Anyone else? Why we take alpha at all?
So if you don't take learning rate small, then it will go zigzag manner from top to anywhere like this.
Yeah, basically it might just overshoot. The actual word is overshoot, okay? The idea is if I start somewhere and if my steps are too big, it can very easily happen that it might overshoot and it might take some more time to kind of settle down, okay? So alpha is usually less than 1. Okay, so you do this in kind of a loop, for loop, let's say. And when do you know to break the loop, or when do you know how to stop the loop? What is the condition to stop the loop?
So when it reach global minima.
No, but how do you know it has reached the global minimum?
We check the change between previous iteration and the current iteration.
Yeah,
The
perfect.
change is not. Yeah.
So the delta, let's say delta is theta new minus theta old. If it is not too much, or if delta overall summation of delta, because there could be a lot of theta, if it is less than, let's say 0.001, then we stop. Okay. Now you will notice something similar will happen in neural networks as well. This is why I started with one of the most basic concepts. Okay. And what happens in logistic regression? If okay, so this is regression, of course. But what if I wanted to do a classification then? So all of this was for regression, statistical regression. What about classification? How do you solve the problem of classification from this idea itself?
We'll go with the sigmoid function.
Yeah, and what is the sigmoid function?
1 by 1 plus e to the power minus x.
Sigmoid of x is, how does it look like if I were to plot this?
Minus.
Yeah, tell me. No need to be shy here, okay? S-shaped, going from where to where?
From 0 to 1.
Minus 1.
0 to 1.
So the minus one thing that you might be mentioning is tan h, okay? Sigmoid goes from 0 to 1 only. So the output is bounded between 0 to 1. Okay. Input is bounded. No, it's unbounded basically. In input terms, it can basically take values from negative infinity till positive infinity. So there is no such restriction. At 0 exactly, at 0, when x is 0, input is 0. So sigmoid 0 is what? What is the value of sigmoid 0?
0.5.
Very good. 1 by 2 or 0.5, as you want to say. Okay. So basically, we have a new hypothesis in terms of, and let me write it like this: theta I t into xi. Okay. Now what should I do here? What is the next step? Again, what is the next step here again?
Cost function.
So can cost function. Give me 1 minute, moment. Just let me connect the charger here. Hey, am I audible? Okay, so what is the cost function here? Cross entropy. What is the cross entropy? Miss, what is the equation of cross entropy? Come on.
One by m sigma I to m.
Okay. Next.
Cos h theta xi.
Sorry.
Cos h theta.
Cos. Where did we get that? What next?
1 minus y theta log.
Yeah, very good. Okay, this is basically binary cross entropy. We many times write it as BCE. So BCE, binary cross entropy. Okay, when you only have two classes, and rest of the steps are same. Again, you will get a gradient, and you will keep updating the gradient. But this how this is gonna work this time? Okay, so fundamentally, what am I doing here exactly?
Classification.
Let's say this is the best fit line. So how does this works exactly?
Classify 0 and 1 like.
Yeah, you're right. But how do I classify here?
So it'll make threshold value above threshold 0 and probability of threshold then.
Okay, very good, very good. So people are saying, as rightfully so, that basically S theta is nothing but when S theta is basically greater than equal to 0. Oh no, sorry, 0.5, my bad. So, okay, fine. If it is 0.5 and if you are saying so, then what would be the idea? Miss, how would it work exactly? Miss, how do you know which classes? So basically the idea is what people are saying is then if class output is y is 1, right? Can you show me graphically, or can you tell me graphically how does it feel, or how do you understand this?
The region above the line is one, like that. Best fit line.
Okay, but why?
That
Because fundamentally, okay, so if I wanted to equate for S theta equal to 0.5, so basically theta or whatever the premise is, internally it should be basically what you are asking is equal to 0, my bad. So what is this equation? Theta I dot xi summation equal to 0. What is this equation exactly? So it's equation of linear manifold. So fundamentally in two dimension, basically it is the exact equation of this. So you can say it is basically y theta I summation transpose dot xi. Okay. What about if I wanted to say something like this, summation of theta I t dot xi? Equation presents. What does this equation represents?
region.
Region, very good. So if we were to analyze this, basically this region, anything up from this line would represent that equation, that the greater sign that you're looking at. Similarly, anything lower would be represented by these gray areas. So basically you will realize that a single line basically divides the overall space in two regions, and this is the whole idea. If when you say greater than 0, basically it is the upper area, and basically you are assigning this as class 1, and whatever is not class 1 becomes class 0. And through estimating a line, you achieve a classification. Seems like a cool idea to work with. Only problem is, by default, it cannot handle nonlinearity. Why? Okay, what is a nonlinear problem? Xor test, okay. Yeah, in stats, one of the most simplest tests is Xor test. And what is Xor test? If I ask you, so Xor is exclusive OR. right? So how does XOR works? Or what is the truth table for XOR? Come on. So when it is false, means your is false and it is actually false then. And when it is true and true. Okay, tell me the output for XOR.
False, false, false.
Sorry, again. Okay, this is false, so let me write it as 0.
And
False, true.
true also false, and false true one means true.
Okay. Everyone agrees with me?
Yeah.
Okay. Now why this is nonlinear? Because if you wanted to replicate this, and let's say in a space, so something like this it will look like. Most probably it will be looking something like this. Now you will realize this, that you cannot draw a single line and bifurcate both of them equally well. Like you cannot draw a single line which can divide both of the classes equally well. And now, do you see the problem? So how do you solve this problem? How do you solve a nonlinear classification or nonlinear pattern recognition?
K means or
Means it's a supervised example. So why would you go for a k-mean example?
SVM or a random forest.
Yeah. Okay. Anything else?
By moving X or star points to a higher dimension.
Sorry. Your voice broke off, so I couldn't hear the whole thing.
Moving into a higher dimension.
Very good. Moving into a higher dimension. There are two ways, guys, okay, to solve this. Either you start with a non-linear hypothesis. So maybe you start with like a hyperbola and you try to fit a hyperbola itself. Okay. Or as Deepak said, you can take a kernel trick. What is a kernel trick?
High kernel reduced.
Again, I did not get the whole thing. So can you say
Like
that
in a
again?
SBM, if you go higher the kernel, it will reduce the dimension from one. It will go to one dimension to another dimension, high dimension, to solve the problem.
Yeah, basically it will introduce more dimensions. So if something cannot be solved linearly in lower dimension, maybe you can solve it in a higher dimension. So let's say if something is not working in 2D, you try to solve in 3D. Okay. So in 3D or higher dimension, you will solve it in a linear fashion, but its projection is going to look like highly nonlinear. Okay. And this is called kernel trick. So there are two approaches. Basically, either you take a kernel trick, basically they are basically very similar, or fundamentally you start with a nonlinear hypothesis and try to fit that itself. Now scikit-learn will of course not allow that, but theoretically you can do that as well, but it's very hard to know which one to do. Now, now here comes the problem of learning. Okay. What is learning and how do we define it in terms of machine learning?
Reducing the error
So reducing the error that you said,
Reducing the error.
in what? Shouldn't you have to define task first?
Yes, okay.
Yeah, means you have to say like there must be some kind of task where you want to reduce the error.
Yeah.
Am I right?
Yes.
Okay. Now the whole problem is, if I have to manually define the hypothesis every time, then it's not much of a machine learning. It's still a lot of human interpretation of the whole idea. Right? You think like which trick is gonna work the best, or you have to think about which kernel function to choose, or if you have to think about which exact hypothesis, initial hypothesis to start with. A lot of stuff, a lot of learning ideas that we are talking is not really starting from scratch if you think about it. Still starting from somewhere, from a human intuition that how to start with to get to the closest answer as soon as possible. Now it sometimes works, but as the nonlinearity increases, as the dimensions increases, ability for humans to think or get or approximate the correct answer also reduces a lot. Okay, would you agree with me?
Yes.
Okay. Now the problem is that, or what we really want to solve is that by combination of simple rules can we solve complex problems. Okay. Now, why we are going after all this? By combination of simple rules, we want to solve complex problems. Why?
Make it universal.
Very good. To make it universal. Look, guys. So in machine learning, there is a concept. I'm not sure. Does everyone knows about this or not? So basically, there is a search for the master algorithm. You understand the concept or the basic idea when I say the master algorithm?
The one which can solve any problem.
Yeah, one with very little tinkering can solve almost any problem. Now, because in CS we like to believe in no free lunch theorem. So what is no free lunch theorem? So I just asked, what is a no free lunch theorem? Come on, someone must know this. Okay, so fundamentally, computer science says this, that no algorithm is inherently better than the other. There's always a trade-off. So it is a matter of trade-off, what trade-off you are doing. Okay. Now this poses a big problem for any master algorithm, that basically no algorithm can be superior from the rest of the algorithms. And neural network also has the same problem. Basically, so far it will be very hard pressed to say that neural networks are the master algorithm or something, because there are also trade-offs that we do have to deal with in terms of neural networks. Okay, so let's start with a very basic idea. Okay, so neural networks. So anyone can basically understand that basically the interpretation must be coming, or the idea must be coming from our own brain, right? So I guess you know that you have your brain or your nervous system is basically made up of individual cells which are called neurons. What are neurons exactly?
That transmits messages from one.
Okay, that would be a rough definition. Anything else?
Sensors, kind of.
Sensors? No, no, come on. No, sensors might not be the best word.
Maybe like some decision making point.
Yeah, so they do both things, okay? They can also transfer and they also kind of make decisions for us. Okay, so this is like a general structure of one neuron cell, okay? Now, again, there are like thousands of neurons in your body, and they can differ in the shape and size as well. But this is like one of the general form that has been accepted. Okay. So let's get down with the idea. How does it works like? Now, the initial idea to mathematically represent neural networks was called perceptron. Sorry. Anyone knows what a perceptron is? So what is a perceptron, guys? So let's say you have inputs, then you have individual weights, and then you have now let's call it a phi. So what is phi here exactly?
Output of some computation.
But can you tell me the computation here?
WIXI plus W1X1
Yeah, so
plus
first let me
W.
put the step function outside because that is of course happening, but internally first sigma will take place and Wi, let's put a transpose xi. This is called a perceptron basically, and so you know what is a step function? It's a very simple function actually. So till you are in 0 or negative, it is 0, and after once you go in positive, it becomes 1. Okay.
One question, why always we use transpose in weights, that is W?
So how would you do the multiplication? Okay, so xi will look like how? Okay, or you can remove x0 if you wanted to. How will wi look like? Let's remove x0 because it would be easier for us to kind of operate. So this looks like n into 1, if I'm not wrong, the shape. How will w look like?
W1, W2, W.
Fine. So let's say W1 till Wn. Okay. Now, if you wanted to multiply them, how would you multiply them? You want a matrix multiplication. So how would the matrix multiplication would work?
Columns of Xi should be equal to rows of W.
Very good, very good. But unfortunately, both of them are same. So how would you multiply them now? Because you understand this is not a conformable matrix or array. So you can't really multiply both of them right now. In their current shape, they can't be multiplied. But if I were to take like WT, W transpose, then it will become W1, W2 till Wn, basically which becomes 1 cross n. Okay. Anyways, you want to process it. Okay. So now you will be able to multiply this. Is it okay? Is it clear with you?
Yeah.
Okay, so that's why we take the transpose. Although when you will do a matrix multiplication through TensorFlow or even NumPy, it's not even required to mention the transpose. It automatically does it. But till we are using our mathematical notation, we should ideally mention that transpose. Okay. Okay. All right. Now, okay. So it's a very simple idea, guys. If this term summation wi dot xi transpose here, if is greater than 0, then it is class 1, and else it is class 0. What does it looks very similar to?
Logistic regression.
Yeah, basically only only thing is we did not use a sigmoid, and of course that's the building step you can see here, right? If I were to just replace this in a single perceptron, if I were to replace this with a sigmoid function, then what it would become? Think, replace this. Think, replace the step function with a sigmoid function.
Logistic regression.
The overall equation becomes like, yeah, very good. Yes, it does becomes very similar to logistic regression. So now the problem remains the same. Now a single neuron or a single perceptron again, it will run into this problem of, even if I replace it with a logistic regression, if I put a sigmoid here and same stuff, if I do keep doing this, okay, again I run into this Xor issue. So you won't be able to solve Xor with a single perceptron. Do you agree with me?
Yes.
Now this is where the idea of a network comes. So does anyone understands what network means? When we understand maybe a single cell or neuron is not powerful, but maybe their connection or their network is really powerful. So do you understand what a network is really?
Connecting different points.
Connecting different points, or let's call them connecting different neurons, okay, in some architecture. So if I were to take a layered architecture, and I will try to show you what is the advantage, but some of you might have done this experiment. If not, you can try it right now. So again, you can take a page, 2D page, okay, so you take a rough page at all, and you convert this rough page into like shape like this, step function basically. That's all I'm asking. So people who have done it, they don't need to do it. Okay. So you will get, so if you will to unpack it, you will see that there's basically there are two lines kind of stuff. Okay. So if you were to again unpack this paper, you will see like there are two lines, but you will understand basically this is nothing. This is just a classification of two areas. Basically, you are getting two kinds of classification based on this. Okay. But what if you take this similar, same structure and you want to fold it again, then what will happen? If I tell you that this folded thing that is already into step function, why don't you fold it again into a step function? So how would it look like?
The two more new parts in
Sorry.
like on the main page again, classification lab, like another two classes will come.
It's just not that. Basically, two classes is not our problem or what we wanted to learn. You will realize that basically your classification line will bend. Just bend your paper twice, and when you will unpack it, you will see that the crease on the paper after the second fold would look like a small bend. Now you will start to see that basically some non-linearity has been introduced if you do it again and again and again. Okay. This is also called hierarchical learning. So our human vision especially does a hierarchical learning. Anyone knows where this idea or what is hierarchical learning? Yeah, okay, but that can equally be sequential learning as well. So what is hierarchical learning?
We combine two things and then
The idea is that any object is made up of, let me show you. So fundamentally, any object is made up of very simple lines and curves. Okay. So if I were to plot this, so the idea is the way your brain works or way mammalian brain works is we always notice the low level features. Low level features mean features with less complexity. We always notice low level features first, and then our brain combines these low level features to give rise to higher level features. Something what you just did on your paper, that if you were to fold it once, you would get like two creases. But if you were to fold it again, you would start to see creases will start to become slightly different. So the idea is very simple, that in one shot, you try not to do all the detection. Okay, so this sorry. So this came from an experimentation by Hubble and Wiesel, and basically in early 1950s, this paper was published. It was called Neural Basis of Visual Perception, and basically they were kind of experimenting on cats' brain signals, and when they saw, and it kind of happened by accident, you know. And there is a good video which I can share with you guys, and the idea was very simple that, sorry. So basically, they were starting to show the sheet, and basically they had like a, so they were trying to do something parallel to the screen. Okay, so they were having a film, and the film was moving up and down and stuff, and it was not doing anything. The cat's brain was not showing anything very particular. At one point, by mistake, what happened is the sheet or the film they were trying to put in the projector was was at a certain angle. So when the kind of reflection came, the reflection came like this. Okay, and there's a video which you can see as well, and immediately the cat's brain started to fire. So then they understood maybe we should not pass straight lines immediately, maybe we should start with lines at an angle, and this triggered the cat's brain, because at its very core level it tries to identify very simple systems, and at certain angles our brain is very optimized to see this, and at, let's say, at 45-degree started to behave, and it started to kind of act on its own. And then they realized that brain, basically, or mammalian brains, actually recognize the simple features first, and then they combine them again and again and again to give rise to very complex features. Okay, so how do you represent simple features? When I'm saying simple features, I'm talking in terms of maths actually. So how do you recognize a simple feature?
Points, line.
Yeah, you can start with a line or linear manifold. Linear manifold is a simple. It can be understood as simple features. So fundamentally what it means is there might be a line that you want to try to detect. Now, any complex feature in your computer is made up of, any complex shape in your computer is fundamentally made up of lines, right? Do you agree? Mm. Let me show you visualization, which will make things very clear for you guys. Let me draw a circle. So for your practical purposes, circle is a nonlinear system. Okay. But do you know your computer actually cannot draw a circle? It cannot actually draw a perfect circle. So let me draw a bounding box at some point so that you will be able to visualize this. So we will mostly focus in this area. Okay. So do you know, like, your computer actually cannot draw a perfect circle ever? It can just give you an approximation or the feel of a circle, but it is never a circle. Why?
Pixel wise, I mean, if we combine a lot of pixels, some are gray or some are, it will, if from outside it will look like a circle, but we zoom
It's a
in
pixel issue. It's a problem, is pixel problem itself. And let me first show you what it looks like. Okay, is it visible? So I'm increasing the zoom so that you can see the problem here. What does it look like now? Now look at the rectangle, it looks perfect. But look at the circle, or any curved surface to be very
Yeah,
close.
it is not able to connect the dots.
Exactly. But you know why that is happening? Let me draw something.
Maybe pi r square. It is
No,
no.
don't worry.
no.
What does this looks like that I have just put here? Point. Now the problem with our mouse pointer is, and you will see this. So this is one of the biggest zooms that is possible. See, this is my mouse pointer. This is how my mouse pointer looks like in Paint. Okay. So even if you try to draw a dot, it is 4 pixels at one point. It cannot go actually even lower than that. Okay, this is the maximum zoom I think I have got. Now the problem is this pixel information. Now I cannot draw anything here because, or maybe I can draw something by using something else. Okay, sorry, not this. I want to do this properly. See this? There are 4 pixels. Now the problem is pixel value. Okay, what is pixel exactly in terms of computer? Pixel value is what?
Matrix.
Sorry.
Matrix.
Matrix. Pixel value itself is an integer, right?
Okay.
Integer or 8-bit representation or a 24-bit representation. Let's call it 8-bit representation for now. Okay, let's call it so that it's easier. Otherwise, we will have to worry about all the channels as well. So pixel value happens to be atomic. You understand what atomic means?
We can't go below it.
Yeah, you cannot separate it. What my point is, if you were to draw a pixel, there would lie only one and only one color inside. Okay, so I'm not sure can you visualize this, but at maximum, each pixel has just one color. Now this is the whole problem, right? Why this is a problem? Let's say you have a set of pixels. Wait. Let me draw it, okay? This might look like grid of pixels. Okay, so if you were to draw a circle, what would happen, guys? So this is a circle. Agree?
Yeah.
Okay. Now let me see if there's a better way to fill this color here. Now everything has to be done by this. Yeah, it looks like. Okay, maybe I can do slightly better. Okay, so how do you represent a circle? Basically, you color that pixel, right? Now, do you see the problem? Anywhere where it passes, I have to color the whole pixel. Even maybe it needs only partial coloring, right? It ideally requires a partial coloring, but I can't do that. This would have been given me the best approximate of a circle, but no. Every time when it passes any pixel, the whole pixel will have to be colored like that. And this is the fundamental issue here that you are seeing. At any point when there are boxes, let's say this is 4 pixels. Okay, all 4 pixels would have to be covered by complete black. What you are seeing the problem here. Do you understand what I'm trying to say? When you see a circle or a curved surface in your computer, in a digital computer, it's just an approximation of that. It's basically constructed by 1 pixel or just a collection of pixels in a straight line. That's all it is. Remember this. Your computer digital computers cannot actually draw a perfect circle or a curved surface. They can't. So what they do is they try to approximate it. Now you think about it. Your circle is made up of lines and pixels. Line is a simple manifold or a linear manifold. But by combining various lines, you get circle which can be or which you can interpret as non-linear. Isn't it interesting? That by combining various lines, you get a circle. So what's the moral of this story? So what's the moral of the story? The point I was trying to make. Does anyone gets the idea?
We can generate any shapes using a simple.
Exactly. When you combine even simple functions repeatedly, we get approximation of complex functions. And this is the most important part that you have to remember. This is why we are using neural networks. The idea is I don't have to design the hypothesis exactly. Maybe the hypothesis is parabolic. We don't do that. We start with linear, and this linear by linear, we approximate the parabolic hypothesis. This is the whole beauty of neural networks, and even in the maths, I will try to show you the same stuff. That's something similar will always keep on happening. So by combining simple functions repeatedly in layer by layer, sequential or hierarchical fashion, we get approximation, or we can get approximation of very complex functions. And this makes neural network a very powerful tool. Because theoretically, again, remember the small demo that I showed you of universal function approximator on Sunday, last Sunday. What is the universal function approximator? Yeah. Let me remove this. Okay. Does no one remember this idea that last Sunday we tried this? So remember this?
Yes.
Yeah, this is what I'm talking about actually. That basically, let it run once. Neural networks, given enough time, enough data, and enough enough layers, they can almost approximate any function in nature. Okay, now I'm using the word approximate, okay, not replicate. So you can see there is a small divergence here in this area, but it works, right? So it is approximately similar to the actual points if you look very carefully. So if you want to try this, although right now the code might not make any sense to you, so still I would like to give you the code once to give it a try. So I'm pasting this on your chat itself. So run this and you can keep changing the function as much as you want. It's totally up to you how much you want to change or how much you want to get it better or something like this. So if you want to apply like something like even a bigger function, and maybe you can also try something negative as well. So negative 50 to 501 or something like this, 51. Okay. So maybe you can try something like this. So you will have negative numbers as well as high positive numbers. And again, you can reshape them, although after reshaping it will look very different. And now by changing the neural network design, by just taking some basic principle, now remember this is a regression problem. So once the training will be done, we will try to do an inverse transform so that we can get the values back. Now you can see there is a very high MSE, which is expected, but you can see approximation still it gets very close. Not always it might not be that close, or maybe it just requires another layer. Maybe if I were to increase the number of layer here, maybe it will work out. So let's give it a try. What if after increasing one layer, maybe it just solves my problem? So maybe let's see if it does the trick or not. So I will use a simple replication and maybe just try to increase the number of layers, but drop it a bit and maybe again use a tanh rather than. So just this gives you a bit more complexity available here. MSC and epoch size is fine, batch size is also fine. Maybe I can use propose as 1 if you want. So this is training right now. Let's see if it approximates anything better or even worse than the previous one. So by putting more nonlinearity, it usually helps our case, okay? So it's done. It will take some time to get that inverse because the network has become slightly complex. The MSE value is still very high, so it doesn't look like it has done much. So it has tried to approximate slightly better, slightly means it has just changed a bit, but it looks like more or less it is doing very similar to what we have done already. So again, by experimenting and by changing some simple rules, maybe starting with ReLU, okay, maybe, or maybe you can start with a Sigmoid. Okay, so by starting and approximating all of this, you might be able to kind of approximate it slightly better. Again, it's totally up to us how do we want to do this. But input dimension is 1 and this is, let's say, if I were to give it slightly more complexity so that it brings down the overall loss. Let's see if it can bring down the loss that fast. Okay, let's see how good or bad it looks. Okay, it clearly has gotten worse now. Yeah, it has clearly gotten worse. So yeah,
what is that epoch?
Sorry.
Some epoch going on. So what is
Don't
that?
worry, don't worry. You will understand a bit later. Okay, no, time has not come for that. A time will come when you will understand all of this. Okay, so basically, what I'm trying to show is, I am just changing some hyperparameters of neural network, and it approximates the function, whatever scale-up function that we give, or like whatever range of the function we provide, and even you can put some noise here. Okay, you can, if you want to, you can put some noise here as well, just to make sure that there is some difference, and still it would be able to approximate the thing. So this is like a very good example that basically neural networks are able to approximate very complex functions in long run as well. Okay. So now this is basically the idea of perceptron itself. So let's say this is the idea fundamentally. So how does the neural network look like? So let me draw something first. So okay, first let me clarify something. So there are a lot of words that people use. Or deep learning, or deep neural networks. What are these? What are all these?
Diagram of input to output, how we are reaching.
Oh no, look, in generic terms, when a person says neural networks, multi-layer perceptron or deep neural networks, they mostly are referring to very similar stuff, okay? Okay, but there are some key differences, especially what is a deep neural network. So, usually in a simple neural network, again I am talking about a network, not a single perceptron. Okay, so this is a simple neural network, okay? Let's say it is, so the first layer is called input layer. It deals with data. So this one will get x1, this will get x2, and so on. Let's say this one gets xn. Let's say this is output. So output 1, output 2, output 3, output 4. Okay. Now there are connections basically. Let's say this is many to one, or you can also think the whole thing as many to many. And it will start to look like a very dense network after a while. Okay, and similarly they go forward. So they all are feed forward networks. This means data always flows forward. And they are all fully connected, and okay, fine. So the first layer is called input layer. This one is called output layer. And all the layers in between are basically, although there are different types of layers, but they can be collectively referred as hidden layers. This could be called artificial neural network, ANN. Okay. So what is a deep neural network all of a sudden?
More than one hidden layer.
Very good. When you have more than one hidden layer, then we like to call it a deep neural network. The idea is basically in deeper layers, once you go beyond one hidden layer, you start to see very complex shapes. Okay. So, okay, let's do one thing. Let's take this idea of deep neural networks, right? So let's look at it.
Yeah, Amritansh,
Yeah.
one question before you move.
Sure.
So like you are asking several questions in between, like related to like sigmoid function and all that. That all is stats ML class, right?
Yes, exactly.
And there are few mathematical concepts which you were discussing. So that all was that all covered in your stats ML classes?
Like, if you can mention which concept, then maybe I can talk about it.
Like
Which one?
something free you were saying, right? Free lunch or like
Uh, yeah,
those kind of concepts.
free lunch is more of a computer science concept. So that's like a pure concept in computer science. So when we learn about algorithmic complexities and stuff, there we are taught no free lunch theorem. But I do discuss that
Right.
in
I'm
my
just
machine learning.
asking because what I have done is I asked Krishna to share your because we were taught by someone else for stats ML, and so just maybe like those are discussed in your classes so better.
May I know, like, yeah, actually I should have gotten the introduction first. Sorry, I totally forgot. Actually, it was supposed to be done last time, but you might remember what happened last time. So I could not have asked introduction from 52 people. So you are from, if I may ask, which batch and when did you complete
Yeah,
this?
I was from stats ML Utkarsh batch.
No, miss, you have to tell me the month or something.
Just now, like maybe 1 week back, like just we finished, then there was a project session, and then your class
Okay.
started.
Good.
Yeah, yeah,
Okay, all right.
yeah.
So, so did you like cover the basics of machine learning and stat properly?
Yeah. We covered. So
Mhm.
yeah, but I will go through your videos as well, just for a better understanding. And so I just asked them the playlist, any past playlist or latest.
Okay. Yeah, there might be a past playlist from
Yeah,
my
yeah.
the batch which I finished in December.
Okay.
So I think that would be a good playlist to watch.
Yeah.
So I do talk about these things because I do find they are very important in the better understanding. Yeah. So yeah,
Right.
okay. People who might not have come from the like any of my batches might find some concept problematic. Although I do kind of discuss them very clearly in machine learning because I do find them they are important. Did you know about this XOR problem?
No.
Yeah, that's like a very fundamental thing. It's like that should be discussed. Otherwise, it's very hard. Miss,
You
right now,
see,
did you understand? Did you
this
understand the
all we
first?
might have read like when we did our engineering, but right now don't remember anything. Like
Yeah,
so
no.
studied so many things, but
Mm,
but that
no,
all
I,
is
I
gone.
agree, I
So
agree.
yeah.
No, but even in machine learning or pattern recognition, it's like at least half an hour introduction is
Yeah,
required.
because in our strats ML, I have revised. Like I am not that great in revision, but yeah, I remember 100% XOR we didn't.
Yeah, but you understand,
Yeah,
like XOR is like one of the
yeah,
most
yeah,
fundamental issue to
yeah,
identify
yeah.
are you dealing with a nonlinear system or what? Or like can you model handle nonlinearity or what? So it's okay, not to worry, but yeah, this is why I was telling like last time that
So your December playlist should be the latest one, right? December 2019,
yeah, I think no,
right?
miss, at that point I ended it, so it might be actually September. So
September to
September to
December. Okay.
December, something like that it went out. So
Okay.
whatever you can
I will
ask them,
ask.
like
Yeah.
for
Yeah. Yeah.
whatever the last one
Yeah.
was, you can just ask
Yeah.
them.
Yeah.
So I think
Okay.
that might be really
Yeah.
helpful for rest
Yeah.
of the
Yeah.
people who are again might be lacking in some of the basics. Okay, because it would take like a lot of time again if I start going through all of them, and we might not be able to focus that much on neural networks then. Yeah, someone
Yeah.
else has a question? Yeah, guys, before I move on, if you have any questions, please ask me right now. It would be like really helpful. You're saying something, or is it just a background noise? Hello? Hello? Okay, all right. I think there was some background noise. Okay, all right, no problem. Okay, let's continue. Okay, this looks like an XOR issue. So you know what I will do? I will kill all the layers. Oh, sorry. I'm just doing the opposite. Not one layer is required, right? Okay, so let's deal with single hidden layer, okay? And I wanted to explain that whatever non-linearity you put, it doesn't matter. It will not be able to solve the XOR problem. Let's put L2 regression and let's provide a very small rate so that it can regularize because, okay, and ratio of training data to test data 70 to 30. Let's put some noise in the data so that it's not that easy to classify anyways, okay? Okay, all right, so this looks like an XOR problem to everyone.
Yeah.
Okay, all right. So let's start with the most simplest one, linear. Now linear is not going to classify this, I already can tell you. And you will see it is not doing anything. There is no change and I should stop this. So here when you go, there is no clear-cut classification line which can define the two groups. So linear is useless. Let's start with tanh this time. Let's see if tanh can solve some problems. So you can see x1 and x2, there are two axes. Okay. So let's see if this can solve the problem. And it looks like it has solved the problem. Okay, almost successfully. So you can see what has happened, that here, first here till here, it is all linear, okay? But if you go here, once you start looking here, you will start to realize it has taken kind of a shape, or basically it has kind of taken a shape, a small shape, in terms of tanh. Okay, so once I put a nonlinear activation function, it is able to solve this, but then I can also introduce something bigger and tougher to solve for it. And then you see tanh kind of almost goes through and almost solves this problem as well. Okay. But if you were to use something simpler like sigmoid, now sigmoid is also non-linear, but you will see sigmoid will have some, it just takes slightly more time to solve the same problem. But you can see that basically it solves these problems. Like binary classification is very easy for it to solve anyways. Let's give it a really hard problem. Let's see if it can solve this. And this is where the limitations start. Now it can be solved. You can increase the number of layers and put more complexity, but this one will not be able to solve this. But what if I increase the number of layers? Maybe also increase the number of neurons that we are looking forward to. So maybe start with more neurons. Let's go sequentially. Let's start with sigmoid. Now even with sigmoid, you will have very hard time solving this. And you can see sigmoid is doing not much here. Okay. Now I can check it out with tanh. It tries to solve a bit, but you can see that only very few of them are getting correct. Okay, most of it is still very wrong, and it's not been able to kind of solve the problem completely. So let's stop this. Now you see that only few neurons get some weights. Okay, like wherever it is, like wherever the weight is very less, like closer to zero, is that neuron is not being used at all. So here, out of these four, only this and this neuron is used, and only this neuron is used in the final two. Okay, or final three actually. And maybe try with ReLU as well once. You will see ReLU will try really hard, and you will see the loss here. You will see the loss will start to drop very fast. And it has almost solved the problem. Almost, I will not say it has been completely solved, but yes. Now initially you'll see when the first layer you will see it is almost linear. Okay, all the lines are linear. But as you go forward now, you will start to see some non-linearity creeping. Means the overall shape has changed. You can see the colors and the groupings. Now it has started to become non-linear. So this is what my point was. Once we put them in layers by layers, it starts to become more non-linear as we go forward with it. Okay. So I will show you with some real-time examples as well that what you can do and how you can solve this problem and what are the design techniques that one has to keep in mind. But this is a very good way to kind of keep practicing all of this stuff and even to have small amount of visualization. Okay. Now, as I was talking about artificial neural networks, I was also telling, or might have been telling you about that what is a deep neural network. So as someone said rightfully, that if you have more than one hidden layer, it is called deep neural network, because basically it can learn very complex representation as you go deeper. Okay. Now, let's start with the most simplest idea. Let your cell be any neuron be like this for now. Okay, I'm taking the most simplest idea. Okay, it's like a logistic. So sigmoid the capital sigma is summation and this sigma is sigmoid function. So what is happening, guys? Now at input layer there is no activation. Remember, okay. So there are 2-3 terms you should know. There is something called activation, which is nothing but it's just a kernel trick. Okay, so when I am saying sigmoid function, here it is just activation function, kernel trick, sigmoid function. Here in this case it is sigmoid, it could be tanh or something else, but here activation function or kernel trick is more or less the same idea. Now at input layer you just have the data. Okay, now we start with the first layer, first hidden layer. Now you have set of wij. Why wij? So I is the set of this number I, and j is set of this number. J is the number of nodes or neurons in the hidden layer, and I is the number of nodes in the input layer. Now remember why it is important. Okay, so can anyone tell me at this layer, at this node, this neuron 1, let's call it neuron 1, how many W's are required? Number of weights. Okay, so number of weights, or W is equal to theta itself. Okay, so whatever in linear regression you have seen, theta I into xi, here the math just simply becomes similar, wi transpose dot xi. Weight and theta basically both are same and interchangeable, but because of neural networks we are saying the word weight. Okay, now can you tell me how many number of weights would be here at this location, only at neuron 1?
N.
Now where is n here all of a sudden? Either there is I or j, where there is n. Look, input layer dimension is I, and the first hidden layer size is j. So now with this term I want to understand. So that at the first node only at the first node, how many weights I have, number of weights. That's I'm asking.
5.
No.
I.
I, because you do not know, it is just like a representation. So yeah, we have I number, and total is how many weights we have. Oh, sorry, how many nodes we have?
J node.
J nodes. So can anyone tell me what would be the structure of W? So basically, it would be IJ. Okay, so let me write it out actually properly. Wij will look like now I into j. So I is number of rows, j is number of columns. Okay. So how does it start? Wait. Let's start from 1, not from 0. Let's start from 1. 1, 1. Similarly, it keeps going W1 j. Now this will keep going down till W I of 1, and this will go till Wi into j. Agree? It will become like a matrix. Now if I were to do this, of course there will be a transpose. what would be the output? If you want to,
WI1,
if anyone is in doubt, xi would look like this. So basically, if you were to take the Wij transpose, so Wij transpose will look like Wij transpose is nothing but Wj into I. Okay. And if you were to multiply this with xi into j, sorry, xi into 1, sorry. So this is
So
conformal.
j by 1.
So output would be j. Basically, there would be a set of outputs, that many nodes, that many outputs. So output 1, output 2, output j. Can anyone just tell me what would be output 1? So for this, you will have to do a matrix.
J.
Sorry.
J. Nothing.
No, output 1.
Okay.
Okay. Think. Wait. Let me explain this. It is easy. Don't worry. It's not very hard. Okay. Let's say these are your inputs. So how many outputs you should get? That many number of nodes in hidden. So this is output 1. So I'm asking what is the equation or value of output 1? This is output 2. And similarly, this is output j. So what is the equation here? Think guys, it's not very hard. So this is x1, x2, 3, and similarly till xn, and all of it is getting multiplied here and of course getting summed up later. So you have to apply a sigmoid here first and then the summation sign. Okay, how does it works now? So imagine the very first connection is W1 1 because this is node 1. Okay. The second connection is W21, third is W31. So the number changing is from here to here. So how is it working? Can anyone tell me? Wi, now this is fixed 1 into x of I goes from 1 to, again I goes from 1 to I basically, or maybe I should write n, yeah, xn. Okay, this is the output at here. Now what is the output at second layer? The second node, sorry. N is equal to 1 to I, again Wi2. Sorry, actually I should write n, sorry, my bad. And so on till the last one where it is sigmoid n is equal to 1 to I W n into j into x of n. See how many outputs we are getting in parallel right now. let's use the matrix multiplication. Okay, maybe if this is not making sense. So wij transpose dot xi, right? This is what I said. Output j is nothing but this equation. Okay, and of course you will have to apply sigmoid over there because each neuron is nothing but sig. Okay, so it gets multiple inputs, multiplies with w and gives the output. Okay, now take the equation. So what is wij? Remember, w11 starts from w1j. Very good. wi into 1 wij. All right, this is the, and then you have x1 xi. Okay, now put a transpose here and multiply both of them. So tell me if you put a transpose, right now it is I into j and this is I into 1. If you were to put a transpose, it will become like, okay, what is transpose?
wji.
Perfect. So it will look like, it will start from w11, but it will go in this direction. And this will become wi into 1. And the last one will be ij as well. Now you are going to multiply it with 1 to xi. Okay, now tell me the output. How does the matrix multiplication works? So the first one, the very first one should look like, again it will look like an array, guys. Okay, straight up array. The very first one will be tell me w I into 1 xi. Similarly, all of the outputs will be written like this. Okay, and of course you can apply the sigmoid after that. Did you get it? What just happened?
Yeah.
If any doubt, please do the maths. Write down the equations. Otherwise, it would be very hard for you to visualize. Can everyone do this basic maths? Yes or no?
Yes.
Okay. Now, the information now in most neural networks, the data propagates in a forward pass. These networks are called feed-forward networks. So for most networks that you will actually study are gonna be feed-forward networks itself. So how is it gonna work? You will have a network. So when I say network, I mean to say neural networks itself. Do not think about anything else. Okay. So start with this. And then the data or the connections move forward in fully connected. So fully connected, when I'm saying this, means all the nodes or all the neurons from the previous one find a connection or have a connection with the all the neurons of the next layer as well. Okay, a lot of people will also refer the same thing as dense connections or densely connected. So if they say densely connected or fully connected, they mean the same thing. And similarly, this layer will outputs will go here.
Can we also say that their weights will be non-zero? I mean, all the weights.
No, there's no guarantee. That's the whole trick, right?
If the weight is zero, then that connection will not exist, right? I mean,
true, and that does happen based on data. So
okay.
This is the whole idea, right? Or not all pathways of your brains. See, there are few connections. This might not be a good example, so maybe take a smaller one. So if you put too much complexity, or like let's say if you have what you have to solve is very simple. So this has not solved it completely yet. Let's say, okay, stop. Let's just see. Let's say it doesn't require this node. Okay. See what is the idea of weights? They are so small that you can almost think. See that there is no depth or there is no width of the lines connecting or outgoing. What it is trying to show is this neuron is almost useless. Even in this network, if this neuron was not there, it would not change the answer at all. Similarly, this neuron is useless. See the weights almost close to zero all the time. So this neuron, this is the whole beauty of it. It can discard neurons if it wants to, if the data, if the classification or regression of data is not dependent on few neurons. That it can dynamically do. That's the best part with it.
Okay. But for a fully connected, it will be non-zero, right? All the weights.
No, look, the connection will be there. It will be very small.
Okay.
But for practical purposes, you can start to think that yes, maybe this connection or some kind of neuron might not exist or might be very weak. Maybe let's say this neuron is so weak that all the connections are very negligible. So data doesn't comes here or neither propagates from here much. Okay, means this neuron might not be contributing to forward pass at all. So it can happen that after training, some neurons are as good as dead. Means they are not serving any purpose. Means there is no data transfer from there.
Okay, got it.
So it can do that, and that's the good part. I told you, no, it can do automatic feature selection. This is one of the it is one of the ways it does it. It can literally kill its own neurons if it wants to, and basically no data passes, so that feature is suppressed. You can, if you want to think it with simple terms, you can think like that, that if something is getting multiplied right here, and after certain training, if this neuron is killed, it might be able to suppress some features altogether. And is done automatically, means not automatically, of course there are mathematical rules, but it's done through data itself. They are observing through data, they are learning through data, and they are killing this information. Clear so far? Any problem? Okay, so by doing this you get till output. What do you think the output will be? Remember, all of your network or nodes are like this. Summation first, then sigmoid.
It will be like a combination of all the equations. I mean, one function inside the activation function, then pass to the next layer.
Yeah, that's fine. But what is the output of a sigmoid value, sigmoid function?
0, 1.
What?
Probability.
Yeah, it's probability. Who told you it was 0 or 1? is the probability value. Okay. We also use another function called softmax for the output layer, which is usually preferred in most of the algorithms. So what is softmax? So for all the classes, get their exponential and divide the sum of exponential. This will give you the probability. So let's say it comes like 0.1, 0.65, 0.25. So what is the output, guys? This is class 0, this is class 1, this is class 2. So what is the output?
Class 1.
How did you get that?
Because it has the highest probability.
Yeah, so basically you try to find the max value.
Max. Yeah.
Okay, whatever the probability array is. And whichever index gave you the highest value, you selected that index, let's say, and your output is class 1, which is not wrong, let's say. Now, but in training phase, what will happen? In training phase, you will get it wrong, right? Again and again and again. So how does it correct itself?
I didn't understand.
Okay, my question is, in training phase, it will be wrong, right? You do understand that part. Okay.
What will be wrong?
The output. Okay, let's make it much complex this time. Okay, so let me show you the power here, that if you want to do the maths, how complex it can become. Okay, so let's mention this one as W1 ij. Let's mention the weights in the next node as W2 jn, and let's mention at output level W3 n into m. Okay, there are m outputs only. So there are I inputs and m outputs. Okay. So can you tell me what is the output shape here, or what is the output here? Anyone you can tell me. Output J is what? Go ahead. Tell me.
Wij.
Careful. Last one is
One. Wij. One.
I. J is okay. J
One.
is anyways the last one.
ij and at the top n.
Yeah, just to simplify things, let's keep it I into this and there too I itself. Okay. So this is the equation at this level, but this is just a sigmoid function which goes here, 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 and here. Now try to tell me what is the output here. So this is output 1. Now try to tell me output 1 of 1. Sorry, not 2. Output 2 of 1 means first node of the second hidden layer. What would be the output? So understand the output here, output J is input for the next layer. So maybe someone can think that it is again same idea. Now if here I is nothing but 1 to J because it is taking that shape, and W will be there. So here W1 was there, here W2 will be there, and it is J to M. Okay, so the J term will change basically this time into O of J. Okay, now what is O of J itself? This equation. Now what will happen at the third layer? If I were to ask you again that at this moment tell me the output, then what would be the output?
Sigma
Very good.
summation J equal to 1.
Let's take n is equal to 1 to
N equal to 1 to M. N. Yeah.
Then
WJ, not J, W N X M. Yeah.
O of 2, because now
O
here
of 2.
let's mention O of 2. Okay, and of course it keeps changing the subscript, so let's mention it as n itself, and this is your output at this layer or at this node. You understand how complex this equation has just become?
Right.
Yeah, can you write the whole equation if I wanted you to write?
Yeah, whole will be.
Okay, let's give it a try. For fun sake, let's give it a try. Okay, the final output layer is final, the output 3 is, and you can choose any one. Okay, is sigmoid. Tell me, it will be really big equation. Sigma W3. Just for simplicity, let's write nm directly. Okay, there of course it goes from 1 to n, no doubt. Now next is, can you tell me? Come on, you guys know this. Into what?
Previous output O of 2. Yeah.
Yeah, O of, but I want you to simplify into its constituents. So you can't write O of n. It would be taking easy way out. So let's take a hard way out now. So if I really wanted to go very hard at you, so what will happen? Sigmoid.
Sigmoid.
Tell me the equation.
J, W of J.
2. It is superscript,
Yeah,
not a power.
2.
And
J of J.
Wij.
M minus 1 or yeah, IJ.
No,
Yeah.
not Wij. Sorry. Again, my bad. Even I should remember all of this. What would be here?
JN.
Yeah, thank you. JN, right? Because JNN. Yes, okay. Now what?
Dot again, sigma.
Very good, thank you. Next. 1 to I.
I equal to 1 to W of I N.
I, J, not
J.
I, N.
I J.
Into. Now let's finish up the parenthesis. See how complex the equation has just become?
Yeah.
You have any idea how complex this equation is already? And see what is happening again and again. Of course, I can change the activation, but let's just keep sigmoid because all of you guys know sigmoid. So look, guys, one decision is made here. So a sigmoid output is given. So sigmoid output is what? Right, some value between 0 to 1. Now this is passed to this equation. Another decision is made which is between 0 to 1. Now again it is passed to this, which makes another decision between 0 to 1. Understand what is happening? It is step-by-step decision. You first decide, is it a line? Then maybe combine few lines and ask. So first let's decide, is it a line, yes or no? Yes, it's a line. Now let's combine few things. Is it a triangle? Maybe this is the second depth output or equation that you want to understand. Maybe you want to understand, maybe the whole thing is a parallelogram or something like that. So at every step there you are making decisions, and what this is doing is it is applying kernel trick again and again, because by every time when you put a sigmoid, you are basically applying a kernel trick. So fundamentally what's happening, guys, then?
Forward pass, as you said.
It is forward. Yes, I totally agree. It's a forward pass. But in training phase, what will be the problem? Okay, try to remember the steps of regression, and tell me what is the problem here. The problem is you don't know this, and you do not know this. So how can you solve for this? See the problem? Is similar to not knowing. It was just simpler over there, no doubt. But it's similar problem, right? That at that point we didn't know theta, what exact theta values were. So if you do not know theta, what you do, and how do you solve regression problem?
Random initialization.
Very good. So what we will do here, we will do random init for this one, and this one, or as many W's you have. What will, okay, so because it is random initialization, of course the output is going to be wrong in the initial days, right? Okay, we are talking about supervised examples only. Now why this is important? Right now we are talking in terms of supervised examples only. Why this is important?
We will be trained with the labels.
No, that's fine. In theoretical terms, why it is important? That is the definition. That's totally fine. But in theory, what difference does it make if I use supervised?
We can know the error, right?
Exactly. Basically, you can come up with a loss function. Unless you don't have supervised, if you do not know the actual y, how can you get error value? That's one of the major differences between unsupervised and supervised. So now you know the error. So again, try to remember the steps of regression would be applicable here as well. So again, because let's say it is a classification problem. So what kind of loss function one should look for?
Log loss.
Very good. Log loss or cross entropy.
Cross entropy.
Yeah, same thing, doesn't matter. Log loss is also called cross entropy. Okay, I hope you remember the equation. So even for a single one, if I just wanted to simplify it for you, even for y is equal to 1, the equation was something like this. Y is the actual one, okay? Log 2 of, let's say the final output 3 whatever the final output is. You wanted to calculate the loss. Now you understand how O3 has been calculated? Agreed?
Yeah.
But again, same problem. But it is dependent on O2 of n, which is
Summation Wij.
no, I think it was
Sorry, Jn.
Jn into
O1. Okay.
take it, all right. But now this OJ O1 itself is dependent on sigmoid
Xi.
Thank you. Xi actually, my bad. Okay. Now tell me. Okay. So once you determine loss function, let's say you choose this loss function as your representative. Okay. Agree?
Yes.
Okay, very good. Now the whole problem is, what do you solve for in gradient descent really?
Mean squared error.
Are you serious? You just
I
said
mean,
yourself it's log loss, right?
gradient
Whatever you
descent
solve,
is right.
no, but gradient descent can be applied on log loss as well, right? It is okay. We take the example of MSE, but even in log loss, so you get these very smooth monotonic curves, right? So I might have shown you that over here as well. You can apply. It's easier to actually apply here. Although the shape is not that easy now. Okay, the shape has become much complex, but of course you can apply gradient descent. Now in gradient descent, what do you really solve for?
Derivative.
No, derivative is the tool, but what do you really solve for?
Reduce the loss function.
Loss? No, loss function is as it is. Gradient descent is not required to solve the loss function. It is just to minimize the loss function. What do you are actually solving it for?
Trying to find the global minima.
No, again, yes, okay, that's the aim. But okay, so fundamentally log loss or your computer has no sense about local minima, okay? It just does the maths. You understand it as local minima or global minima. Computer doesn't knows local minima, global minima. It just knows how to do the maths very fast. That's the only thing it does. What are you actually solving it for?
We are finding slope at each point.
But what are you really solving for?
Direction.
Direction for what?
To reduce the error, to find the minimum.
Guys, you are trying to solve for theta actually. Remember this gradient descent is steps. You have forgotten gradient descent steps really fast, okay? So what are you solving for? Theta, right? At the end, gradient descent step is for theta, solving theta. Now tell me, I am having 3 W's. So if I do error correction, which W I will be solving for? I have 3 sets of W's, right? 3 sets of weights. So if I apply a gradient descent here, again, it's a classification technique, right? I just decided cross entropy should be my loss function. So I should be able to apply gradient descent. So if I apply gradient descent, I will be solving for which weight or which set of weights?
First it will be W3, then W2 and then W1.
Exactly, but W3 is dependent on this equation and this equation is dependent on this equation. So even if you solve for W3, you are still in a big problem because W3 is going to get multiplied by this, which is based on a W2, which again comes with this equation, which is again dependent on W3. So how do you assign the blame or how do you decide which is the problem or where the problem lies? In an organization, in a software development, when a product release fails, who gets blamed first?
Employee.
No, come on.
Director,
Yeah, some higher order. And
like
then,
top to bottom.
yeah, top to bottom, the blame starts, right? Let's say CTO or someone will get the blame first. Okay, whoever was in charge, they will find the managers. They will scream on the managers. Managers will scream on the team leaders, and the team leaders will scream on testers or coders. Like it's a very hierarchical order of things happening. You have to imagine the same thing here as well. One second. The idea is, if something goes wrong at the output final output layer, the error will be propagated or error has to be assigned from the behind. Means W3 error has been caused because of W2 error. But W2 error itself has been caused, maybe has been caused because of W1 error. It can happen because of multiple reasons. I will explain you the reasons as well. Okay. So one reason is randomness, because you started randomly, so of course they will be wrong. Means there is a high chance they will be wrong. Maybe W3 is wrong because W2 was wrong, or maybe W2 is wrong because W1 is wrong, or maybe the last one is data inconsistency. Maybe the problem is with data, it's not the W, but let's not worry about data inconsistency right now. Means there could be errors in data which you cannot reduce, so nothing can be done over there. But let's find a simple blame thing, that issues in W3 final output that happened there happened because of W2, but issues in W2 might have happened because of W1. So how do you assign all of this blame correctly? So I would like to stop here today. Okay, I will not tell you the answer right now. I will not tell you the answer tomorrow. So I want you to think on this one. Okay, I really want you to think on this one, and I will give you a homework today. Again, you will have some time, but try to solve the error issue first of all. Think how would you solve for this error problem, because now you see the problem. W3 is dependent on W2 and W2 is dependent on W1. So if something is wrong at level of W3, who is to be blamed? Right? So this is gonna be your problem statement, and I want you to solve for this one. Okay, any question before we close down today? Today's session. I know you must have a lot of questions, and please ask them right away. Or you can take some time, and maybe tomorrow you can also ask me.
But if you, sorry to disturb you, actually if you take derivative, then error will be reduced, no?
No, but that's true. But okay, let's again have the same discussion in your head and think very carefully what I'm trying to say. You are trying to reduce the error, but remember over there, theta was not dependent on something. Okay, so imagine these three as variables. W1 is a variable, W2 is a variable, W3 is a variable. Okay. Now you are trying to solve for W3, but W3 itself is dependent on W2, which happens to be a variable, and W2 when you try to solve for W2, which is again dependent on W1. So you will assign the blame on whom? Try to think, all three are variables here. So if you try to solve, so far what you were trying to do was like you were trying to for theta. Now theta was not dependent on any other variable. Based on data, you could just update theta, right? And whatever the gradient step was. I'm just telling you that W3 itself is dependent on W2 and is in turn it is dependent on W1. So if one variable is dependent on other and the other is dependent on something else, how would you solve for that? Gradient descent is of course going to reduce. That's not my issue. My issue is if these are dependent on each other, then blame assigns the credit assignment or blame assignment goes how? Like how would you assign the blame? That's my question.
I think in both W2 and W1 will modify.
No, but which one is more to blame? How do you know that?
We'll start from W1.
But how? Your error calculation? Error can only be calculated at here itself. So you cannot start at W1. Unless you do not compare with some Y output, how would you know the error? But if you have calculated the error here, how would you know the error here?
Back propagation.
Very good. If people already know, don't discuss. Let other people think on their own, okay? So basically this is the fundamental, so foundation of backpropagation, but let's discuss this tomorrow.
Okay.
Let's not put it tomorrow today. I want people to think on their own first. And if you come up with this explanation, amazing, it would be really easy. Otherwise I will Okay, if there is nothing else, I would like to stop the session. I will be sending you an assignment.